So, hello everyone. It's our pleasure to have Yuxuan here to share about his recent work with us on efficient learning of for linear properties of quantum circuits. And Yuxuan, the floor is yours.
Thanks for the introduction. Hello everyone, I'm Yuxuan Du from the College of Computing and Data Science, Nanyang Technical University. It's my great pleasure to have this opportunity to share our recent work, efficient learning for linear properties of quantum circuits. This work is joined with Minxiu Xie and Dacheng Tao. Before presenting our main results, I'd like to first introduce some key motivations and backgrounds of this work. The first key motivation of this work is that how to understand the large-qubit quantum computers. Before answering this question, we need to figure out what are the large-qubit quantum computers. Roughly speaking, I like to specify the quantum computers with about 55 qubits as large-qubit quantum computing devices. This is not a rigorous definition because even for a quantum computer with about 55 qubits, we can still devise some clever methods to simulate their behavior. But in general case, we can no longer use state vector simulators to capture the exact dynamics of these quantum computing devices. Meantime, we need to only use these clever methods to simulate specific quantum circuits or some noisy quantum circuits. So I like to specify the large-qubit computing in this talk as a quantum computer with about 55 qubits. And according to this definition, we can see several quantum architectures have already stepped into this region. The first one is a superconducting quantum computer. Since 2019, where quantum AI has demonstrated the quantum tomography in a random sampling task by using their 53-qubit quantum computer. And in the following, in 2023, IBM has released a superconducting quantum computer with about 1,000 qubits. And just recently, Google Quantum AI has used their newly fabricated 101 qubit quantum computer to show the effectiveness of quantum action. Another architecture has stepped into the large qubit quantum computing era is reconfigurable atom arrays. In the earlier of this year, QEra has demonstrated how to use 256 qubit reconfigurable atom arrays to demonstrate the effectiveness of quantum error correction. So the rapid development of quantum hardware motivates us to rethink how to understand the behavior of large qubit quantum computers. The challenges in this topic are from the fact that traditional methods which can be used to understand the behavior of small qubit quantum computers may not be applicable to understand the large qubit quantum computing devices. As we can see in the plot, there are two approaches of the traditional methods. The first one is the tomography-based approaches. Another one is classical simulators. For the tomography-based approaches, such as quantum state tomography, quantum process tomography, or quantum gate set tomography, they require computational cost generally exponentially scales with the number of qubits. This means that these tomography-based approaches can only be applied to the quantum computers within 20 qubits. Otherwise, we will encounter the memory issue or runtime issue. One exception is the shadow tomography, which can be used to understand the behavior of large qubit quantum computers. But we need to note that shadow tomography is resource intensive. This is because in general, we want to capture the information or properties of correlated quantum states. But shadow tomography cannot identify these correlations. We need to repeatedly apply shadow tomography on individual states, and this is quantum resource intensive. But as we know, currently quantum computers are scarce, so we need to control the use of the quantum computing to get the derived properties.
May I know why you consider the system larger than 45 qubits?
I showed the reason in the first slide. This is because this is not a rigorous definition. What I mean is that when the quantum system size is beyond the 45 qubits, you can no longer use state vector simulators to capture the dynamic of the quantum circuits. You can either devise some clever simulator methods, but these simulators have certain limitations, and I will later. And so this is a rough definition. So anyway, if you want to understand behavior of 55 qubits, you need to pay expensive costs.
Basically, you mean if you have a supercomputer,
yeah,
and you use it for the quantum simulation, you can now you can simulate up to the 45 qubits,
yes,
or something like that. Yeah.
yes. And for the classical simulators, as I said before, if we want to use state vector simulators, we can only apply to the quantum system within 55 qubits. Otherwise, we will encounter the memory issue. Although there are some more clever methods like tensor network or Clifford simulators, which can be applied to larger quantum systems, they have their own limitations. For example, tensor network cannot simulate high entanglement circuits, and the Clifford simulators cannot simulate quantum circuits with non-Clifford gates such as T gates. Having witnessed the limitation of the traditional methods like tomography-based approaches or classical simulators, it's necessary to develop novel approaches to help us under the behavior of large qubit quantum computers. And this novel method should satisfy two requirements. The first requirement is that the proposed method can efficiently simulate more states compared to the classical simulators. For example, it should be efficient in estimating the properties of high entanglement states or the quantum states composed or produced by the non-Clifford gates. The second condition is that the proposed method should use fewer quantum resources compared to the tomography-based approaches. Okay, now let's turn to the second motivation, which is from the recent advancement of quantum learning. So, if we shift our attention from understanding the behavior of quantum circuits to understanding the behavior of ground states in quantum many-body problems, we already have some novel methods. The seminal work in this research line is completed by Dr. Huang in 2022. He solved the following problem. Suppose we have a class of Hamiltonians by hx. Here x is the classical parameters such as the strength of the different spins. He devised a machine learning method to say that we can efficiently predict the properties of ground states in this class of Hamiltonians efficiently. And the learning pipeline is shown in the dashed box. The learning process consists of two stages. In the first stage, the learner just randomly sample different x and feed this x to the quantum system and produce the corresponding ground states. Once the ground states are prepared, the learner applies the poly-based shadow to collect information from quantum systems to the classical memory. In this process, by repeating this process, we can form a training data set, which is composed of two parts. The first part is the classical parameter x, and another part is the obtained classical shadow information of the ground state of hx. Once the training data set is prepared, the classical learner can use this training data set to form a classical learning model, which can be used to predict the properties of ground states of new x. And it was noting that in this learning process, the learner only need to interact with the quantum system in the first step. Once the first step is finished, the learner no longer needs to interact with the system. And the efficiency of the learner is warranted by a specific setting. Rotterdam proved that when the learner Hamiltonian hx satisfies certain conditions, such as smooth properties, which means that the Hamiltonian should satisfy certain sparse or local structure, or the Hamiltonian is gapped local, then we can use polynomial samples and runtime. Here, polynomial scaling with the number of qubits or the dimension of the classical control x to get a good prediction. But it was noted that the results of this paradigm cannot be straightforward to the quantum setting, because the restrictions about the smoothness of Hamiltonians cannot be straightforwardly extended to the quantum circuits. And for the quantum circuits, there has some empirical success. In recent years, different research groups apply deep neural networks to enhance our understanding of large-qubit quantum circuits, including quantum error correction, entanglement estimation, and cross-platform fidelity estimation. But all of these works have a common drawback, which means that they do not have a theoretical guarantee, which means that we do not know what kinds of data types should be used in the training process. We don't know what kind of learning models are optimal, and we do not know how the prediction error scales with the number of qubits, number of training examples. So it's necessary to develop a properly efficient learning method to answer this question. So combining the above two motivations, we can raise a critical question. That is there any efficient classical machine learning model under some practical conditions that can well predict the linear properties of large-qubit quantum circuits? Okay, this work aims to answer the question by focusing on a specific universal data set, which is composed of rotational Lie gates, RD, and Clifford gates. The circuit setting is shown in the left panel, as we can see for the quantum circuit. The input quantum state can be arbitrary, and the quantum circuit is composed of DR gates, DRD gates, and G minus D Clifford gates. And the measurement is restricted to the local or incoherent measurements. And the learner can only access to the quantum system by feeding different rotation angles of RD gates. And he can only receive the measurement results by applying the incoherent measurements. By collecting the measurement results, the learner needs to train a model that can efficiently and accurately predict the linear property of these quantum circuits with different rotation angles. And in the prediction stage, the learner cannot access to the quantum system. So how do we define efficiency? Here, the efficiency represents the computational complexity during the training and the inference stages should be polynomially scaling with the number of qubits and the dimension of the classical parameters D. Okay, the achieved results by answering this question have many implications. The first implication is to enrich quantum learning theory. Currently, we know there exist efficient learners to learn T-dot Clifford circuits, graph states, and ground states under certain cases. Here, the classical learner refers that the learner can only access quantum systems during the data collection stage, and the learner cannot access quantum systems during the inference stage. And for the quantum learner, which means that the learner can access quantum systems during the prediction stage, we know the quantum learner can sample efficiently learn the dynamics of quantitative circuit, including the state, the unitary, or the linear properties of the quantum circuits. But it also proven that even for the quantum learner, it can be computationally difficult to predict the dynamics of quantum gate circuit. So our results can enrich the quantum learning theory about this issue. And the second implication of this work is to deliver practical applications. As we can see in most applications of modern quantum computers, such as quantum verification, quantum shadow estimation, Hamiltonian simulation, and variational quantum algorithms, they all involve estimate the linear properties of quantum circuits. If we can devise an efficient classical learner, we can significantly reduce the quantum resources to complete these tasks. The third implication is questioning the frontier of quantum computing. As we know, signal to identify the practical utility or advantage of near-term quantum computing is showing that the quantum computer can outperform classical simulators in the measure of accuracy, runtime complexity, or symbol complexity. But if there exists an efficient classical learner, we need to rethink how to define the quantum advantage or practical utility from computers. Okay, now let us show our main results. We need to first formally define the problem we studied. Actually, we studied encrypted quantum circuits, as shown in the left panel. The input state is arbitrary and is denoted by rho 0, and the export quantum circuit, which is composed of DRD gates and G minus D Clifford gates, is denoted by UX. And the produced or generated state after applying UX to the input state rho 0 is denoted by UX. And what we want to learn is a concept class denoted by curly F. It refers to the trace of rho x times an arbitrary observable O. Here we need to apply some conditions of the observable. The observable should satisfy two conditions. The first condition is that the summation of the effective norm of OI, which means the local observable, should be upper bounded by B. And the local observable OI, the maximum locality of the local observable OI should be upper bounded by K. And our purpose is to design an efficient classical learner that can output a hypothesis HXO, which has a low prediction error. The prediction error is measured by the equation in the red box, which means that the difference between the prediction and the target value on average would be upper bounded by epsilon. And to achieve our central aim, we need to separately answer three sub-aims. The first two sub-aims are answering the analyzing the sample complexity and the computational complexity to learn the concept class curly F. And the third sub-aim is to design a detailed algorithm that can be used to predict the concept class of curly F. In the following slides, I will just show you the basic intuitions to achieve these three sub-aims. you can wrap to the manual script to see our proof details. Now let us see how to achieve the first. To achieve this goal, we need to separately analyze the upper bound and the lower bound of the sample complexity to achieve the epsilon prediction error. To achieve this goal, the main technical tools are carving and packing net, the hypothesis testing, and the final inequality. To achieve the lower bound, which means that the training examples is necessary to obtain epsilon prediction error, we construct a 2-qubit circuit as shown in the upper panel. As we can see, this circuit is composed of SWAP gates and RZ gates. And the initial state is the product state, row 0, tensor products 0 state. And the formal definition of row 0 is shown here. It's a 2x2 matrix. A good property of this circuit is that we can write down the analytic form of each target concept f(ax), as we can see it's actually a cosine function. And another good property of this circuit is that for any pair of concepts in the class, they have equal distance, which is 2 times epsilon times b squared. This means that the distance of different concepts is sufficiently large. This means that learning this concept class is relatively difficult. For example, if all concepts concentrates one point, then this concept class is easy to learn. We just need to find a hypothesis to predict a constant, then we can get a low prediction error. So based on this construct circuit, we can set up a hypothesizing task. In the first step, Alex picked up an index A from 2 2D candidates, which is from 2 2D concepts. And then in the second step, Bob collects training data set based on the selected target concept at base star. In the second step, Bob cannot see the analytic form of the target concept. He can only obtain the estimation of f base star xi by using finite snapshots. And in this way, he can build up a training data set with 10 training examples. And for each training example, it consists of 2 parts. The first part is the propagation angle of RZ gates by xi, and the second part is the estimation results denoted by hat O A star I. And in the third step, Bob finds hypothesis by using the collected data set. They just need to conduct minimization problem, optimization problem, and obtain a hypothesis denoted by H tau. And in the last step, the Bob needs to use the inferred hypothesis H tau to find an index with the close distance with this hypothesis. And this index is denoted by R(A). And the prediction error between A star and A bar can be bounded by the final inequality shown in the bottom. In other words, we need to separately analyze the upper bound of the mutual information between A star and the estimated A bar, and the cardinality of the concept class to obtain the sample complexity. And we can prove that the mutual information between A star and A bar is upper bounded by this term, and after some simplifications, we can obtain the lower bound of the training examples to learn the quantum circuit. Okay, now we turn to analyze the upper bound of the sample complexity. And this bound is rooted on the results of Huang work published on PRL in 2021. In his work, he shows that in our setting, which means when we use a classical learner to learn a quantum circuit, the training example, when the training example satisfies this inequality, is sufficient to get an epsilon prediction error. And our key contribution here is to calculate the upper bound of the for epsilon packing net of the concept class F, and we can obtain upper bound. And by combining these two results, we can obtain the upper bound of sample complexity to learn the class KDF. And now we move to the second subway, which is to analyzing the computational complexity of learning the concept class KDF. And this proof is rooted on a recent work published by Virgin Dunkle in that's maybe 4 months ago, and he shows that he proved the limitations of offline learning, which means that if a classical learner can only access the quantum system during the training stage, they prove that based on some complex theory, they prove that no algorithm that can solely use the collected mechanism results will learn a concept class in a polynomial time. And the concept class we built is based on can be easily adapted to our setting, which means the circuit composed of RD gates and Clifford gates, so we can easily mapping their results to our results. So based on the results of two sub-aims, we know if we want to learn, if we want to use machine learning to predict the behavior of large-qubit quantum circuits. In general case, it can be simply efficient, but it may be computational hard. So this means that we can never find an efficient learning algorithm to predict arbitrary quantum circuit in an efficient way. But in the following, we will present an algorithm, a machine learning algorithm that can efficiently predict a specific class of quantum circuits with practical interest. And the learning pipeline of the proposed learning model is shown here. It also consists of two parts. The first part is data collection, and the second part is the model construction and prediction. In the first part, I mean the data collection, the learner just uniformly sample different rotation angles xi and feed them into the quantum circuits, and the learner applies the poly-based shadow to obtain the information, to extract information from quantum circuits to the classical memory. And in this way, we can build the training data set with n training examples, which is composed of two parts. The first part is the sampled rotation angles xi, and the second part is the classical shadow informations denoted by tilde rho t. T refers to the number of snapshots of poly-based classical shadow. Once the data set is prepared, we can build a classical kernel to complete the prediction. And this classical kernel is composed of two parts. The first part is mapping the rotation angle in a high-dimensional space by using different cosine and sine functions. Another part is the estimation result, which means that we need to use the collected shadow estimation tilde rho t to get the estimation of the target observable. And the detailed formalism of the learning model is shown here. As we can see, the HS, I mean the proposed machine learning model is composed of two parts. The first part is kappa lambda, which is called a truncated trigonometric monomial kernel. And the second part is the shadow estimator, which is used to estimate the target observable. And the detailed formalism of the truncated trigonometric monomial kernel is shown in the dash box. As we can see, it's a linear combination of some trigonometric monomial bases with proper scaling. And why we say it is truncated, because we only focus on the low weight frequency, which means that if the sampled omega has many 1 or -1, we need to remove it. We only consider the spectrum or frequency with low weight, where many of the entries in the omega should be 0. And the second part, I mean, the shadow estimation just applies the Q routine as the classical shadow state of the S-training example on the target observable O. There are two important results of the proposed model. The first one is unbiased state estimator, which means that if we slightly modify the proposed machine learning model, which means that we substitute the shadow estimation part with the original reconstructed classical shadow state, we can prove that the predicted state pattern sigma x is actually an unbiased estimator of the predicted state rho x. And this means that if we set the truncation number big lambda as d, then on average the predicted state hat sigma x is equal to rho x. And another result is that under certain smooth condition, which means that the norm of a gradient trace rho x O upper bound by C on average, we can show that the training example, the sufficient training example is satisfied this inequality. This inequality does not explicitly depend on the number of qubits or the dimension of the classical parameters. It only depends on the upper bound of the gradient norm. This means that for certain cases, we can find some efficient. We can use our post model to efficiently predict the linear properties of circuits. So when the gradient norm can be well bounded, an extreme example is Baron-Plateau, and in many papers they prove that when Baron-Plateau happens, the constancy will be exponentially scaled with inversely exponentially scaled with the number of qubits. This means that the constancy will be sufficiently small, and the quantity, I mean the cardinality of the ball times 3 over epsilon will be very small, and then the required number of training examples will be very small, and then we can find the proposed machine learning model is very efficient, because in this case the required number of training examples n will be very small. It may be independent with the number of qubits or the number of or the dimension of classical control parameters, and the classical shadow information can be efficiently stored, and we can efficiently calculate the kernel kappa lambda and the shadow estimation G, and we can claim the proposed learning model is computationally efficient. In another scenario, which means that we have a quantum circuit with many Clifford gates, but just a few not Clifford gates, just a few RG gates. We can set a full expansion, which means that the truncation number do not be. We can use full spectrum. We don't need to apply any truncation, and we can achieve accurate prediction with an efficient manner. And these results can deliver many interesting practical applications, including quantum certification, shadow estimation, and variational quantum algorithms, as I will be showing later. Now I will show some intuitions why the proposed machine learning model works. To answer this question, we need to reformulate the concept class by using the polynomial matrix. The definition of the polynomial matrix is shown here. For the state of observable, we need to expand it. There is a poly basis, which means that for any quantum state, after applying PTM polynomial matrix, we can obtain a vector with 4 to n dimension. And for unitary, after applying PTM, we will get a new matrix with the size 4 to n times 4 to n. And an example of RZ gate is shown here. When we apply PDM to the RZ gate, we will get a matrix with the size 4 times 2 and 4 by 4. And this matrix can be decomposed into 3 parts: D0 plus cosine xi times D1 plus sin xj times D2. And D0, D1, D2 are fixed matrices. So this is why we say we can build a trigonometric nomorial kernel, because we can see due to the property of PDM, which means that when you have two unitaries, as shown in the upper right side, if you have 2 unitaries, lambda 2 and lambda 1, when you represent it under the PDM, you can see you just need to consecutively apply this to their corresponding PDMs. So we can, based on this formula, to see we can always write the target concept of the quantum state ρx by the PDM formulation, and this formulation will allow us to get the trigonometric basis.
Sorry, I have a question over here. Is this the only way for us to decompose?
No, this is not the only way. Another way, you can also apply other transformations, such as you can use like Fourier transformation to decompose roots into a certain basis. But in the work, we use a poly basis.
Like, why do you consider poly basis instead of the Fourier basis? Robert Huang considered in his paper, right?
Yeah, because Fourier basis, I think the Fourier basis is not compact, because when you use Fourier basis, the spectrum of omega will be very large. In this case, the spectrum of omega is 0 plus 1 minus 1 over d. But in this case, the spectrum is on the whole integral space. So you will have wide spectrum, and you don't know how to get up over truncation. The difficulty comes from the how to truncate it. But if under poly-based expansion, we will see how to connect the smoothness property, I mean the upper bound of the gradient norm of the truncation. I mean the width of the spectral norm. Spectrum, yes.
Right, I see. Yes.
Okay, under the PDM formulation, we can answer 2 other questions. Is the first one is why truncation works. Another one is why kernel works. Why truncation works? Why we can truncate the high weight frequency and only preserve the low weight frequency to make the proposed machine learning works. This is very important, because if we cannot apply truncation, we need to calculate the whole spectrum, which scales with which exponentially scale with the dimension of classical controls, maybe 3 to d. So for log d, we can no longer get an efficient method. So truncation is very important. But why truncation works, and the result is shown here. That is, when we calculate the truncation error, which means that the difference between trace O rho lambda x minus trace O rho x under the expectation value, we can say we can obtain the right-hand side result, which goes to the linear combination of trace rho omega O with proper scaling. And by applying the inverse Fourier transformation, we can see the results, the value of trace rho omega O equals to this quantity, which goes to 2 to the zero norm of omega times this quantity. And you can see this 2 quantity will be cancelled. And when we take expectation of the trigonometric basis by omega x, if you have a high weight private basis, which means that most of the coefficients in the basis rho omega x equals to sin xi or cos xi, it tends to be zero under the expectation of under the uniform expectation. So it will be cancelled. So this is an important property to ensure we can take truncation. And why kernel works? In other words, why learning works? Actually, the essence of learning is mapping the original data into a high-dimensional vector space with the interpolation property, which means that on the high-dimensional space, the training examples and the unseen examples can be well interpolation. And we can see based on the PTM formula, we can see all training state or all quantum state rho x can be represented by coefficient of omega phi omega x times high-dimensional vector rho omega. And rho omega is independent with the classical parameters. So when we see this high-dimensional space, we can calculate the similarity between the training example phi omega x and the new example phi omega 4 phi omega x prime to calculate some similarity to conduct the prediction. But the issue is that in the original formalism, the basis is denoted by rho omega. We don't know the explicit form of rho omega. But actually, there is a close interconnection between rho omega and the shadow estimation, shown in the lower right panel. When we take expectation over the training examples under uniform distribution, we can see the value of trace rho omega O equals to the shadow estimation trace rho XO with some scaling parameters. So this makes that we can transfer the support rho omega to some result of shadow estimation. So this is why the proposed learning model composed of two parts. The first one is the truncated kernel, and another one is the shadow estimation. Okay. Now let me show you some proof scratch. Actually, we can achieve our result by decompose the prediction error into two parts. The first part is the truncation error. As I mentioned before, we can use the smooth condition to connect the truncation error with the upper bound of the gradient norm. In this way, we can say the truncation error is upper bounded by C over lambda. And for the estimate error, it mainly comes from the shadow estimation. So by using the result of poly-based shadow estimation, we can obtain the estimation error in our case. And by combining these two results, we can obtain the required sample complexity to achieve below prediction error. And our work also analysis achieve two-side results. The first one is that if the number of RD gates, I mean the number of D is not so large, we can replace the quantum system to a classical simulator. Actually, we just need to capture the estimation of trace rho XIO. If your quantum circuit only consists of a small number of RD gates, we can find some Clifford class T simulators to achieve this goal. In this way, we can also obtain a bound to ensure our proposed learning model is efficient. As we can see in this case, the required number of training examples is exponentially scaled with the number of RD gates 3 to D, but in certain cases, it maybe have independent interest. Another case that our result can be generalized to any rotational poly gates plus Clifford gates, which means that we can replace RD gate to any rotational based strings, and our results still hold. Okay, we conduct 3 simulations to verify the effectiveness of our proposed learning model. The first one is to predict two-point correlations of 60 qubit rotational G-d states. The contraction of the J state is shown in the upper right panel, which means that we first prepare a J state and then apply the Y gates on the first qubit, the 30th qubit, and the last qubit. And when the state is generated, we apply a two-point correlator Cij. Here, Ij refers to any pair of qubits among 60 qubits. Under the lower left panel, that must be results when we set the information length as 3 and the snapshot for each training example at 1000 with 30 training examples. And we can see the prediction result and the exact values are almost the same. And we also conduct ablation study to understand the performance of the proposed learning model. We consider different number of qubits, different truncation values, and different snapshots per training example. But we fix the number of training example as 500. We can see in this case, even if we set the truncation number as 2, maybe we ignore the most high weight frequency, we can obtain similar performance with false spectrum for expansion. And if we think much more, we set the truncation value as 1, we can say there is a high prediction error. And in the second simulation, we verify the effectiveness of our results by predicting the properties of states evolved by 6 qubit global Hamiltonian. In this case, we substitute RD gates with a rotational high polystring, rotational high polystring. And so in the equation is 2e2 minus imaginary unit times xj times tensor product from first qubit to the last qubit under the poly basis. And we set different settings, I mean different number of rotational gates. The lower left panel shows the results when we set the number of rotational gates at 1. We can see by slightly increasing the number of training examples from 10 to 20, we can get a very accurate prediction. But the result is not very good when we set the number of training example, set the number of rotational gates as 30. In this case, I think we need to set much larger truncation values to obtain a good prediction. But we encounter some memory issue in this setting because storing the classical shadow informations of 6 qubit circuits is relatively costly. The last case is using our results to enhance variational quantum algorithms. The key philosophy is using pre-training method, which means that we just need to collect data of hardware fit assets and train our prediction model. After our model is trained, we can use it to optimizing different assets by optimizing these assets under different tasks, which means that we can use this learning prediction model to optimize the ground state properties of different Hamiltonians, or use it to optimize quantum networks on different classification tasks. And after offline optimization, we can use the optimized parameters as the initial parameters on the fine-tuning stage. And here is the simulation results of our proposed learning model on 3 qubit case. We use it to find the ground state energy of transverse field EC model. And as we can see, when we set the truncation number at 7 and the training examples as 90,000, it can get a very accurate prediction. And the convergence rate is shown on the right left-hand side panel, and we can see it can be the conversion rate is faster than the original VQE. This is because the proposed learning model will output will predict the results with some randomness, and the randomness or the error is a good thing in stochastic optimization. So in certain cases, it will ensure faster convergence. Now let me conclude this talk. There are many interesting future directions. For the quantum learning theory, it's interesting to explore how the learnability of quantum circuits when they have correct parameters. And another one is from the average case to the worst case, because in this work we only analyze the learnability of the classical learner in the average case, but it's an open question about the worst case. And the third question is the online learning paradigm, which means that if we can allow the quantum resources in the predict stage, how the learnability or the power of the learner can be changed. From the practical side, our results, there are three interesting future directions. The first one is how to design an efficient learning model that can predict the result of noisy quantum circuits. And the second one is how to devise a properly efficient learning model to predict nonlinear property of quantum circuits. And the last one is how to design a learning model beyond the uniform distribution. And all of these results can deliver significant impacts on different practical applications. Okay, here are all the contents I'd like to share with you today. Thanks for your listening.
Thanks, Yuxuan, for the very detailed talks. For people here, you can just ask questions, and for people online, you can just unmute yourself, ask the questions, or type the question in the chat and ask. So I think I could start with me. Will you go back 2 slides earlier on the conclusion? Yeah, this one. So what do you mean by Q-info? Is it like just like quantum information theoretic bounds on their result?
You mean the second column?
Yeah, the second column.
This means that if we can access quantum system during the inference stage.
Oh, inference. I see. I thought it's quantum information. Yeah, I have actually a couple of questions over here. So you in the numerics, you say for 60 qubits it's actually very costly for you to store the classical shadows informations.
Yeah.
Like how much? Like how expensive is it? Because I always thought it's very cheap.
I think it's because we optimize the storage methods. Actually, the shadow information is just binary bit string.
Right, yeah.
But actually, when you derive it, it will transform it to the float points. So you will have almost 16 slowly. So maybe if you want to save maybe 10,000 training examples, the corresponding storage memory should be 60 GB. So it's
okay.
So it's very large.
Oh, okay. I see. So it's coming from like converting to the floor, and then and then oh, I see. Okay. And actually, there's one very kind of like naive questions over here is that because you kind of explicitly construct the model, right? So you I like similar to actually it's the same question for Robert paper as well. Over here you just have an explicit machine learning model for the prediction, but it don't really involve any training, right? Like the typical training that we do, like gradient descents and things like that.
Actually, you can select this model to the like lasso or ridge regression, which involves a gradient descent.
Right.
Because there is equivalence between the kernel methods and the regression methods. Yes. So you can easily transform the learning model to the regression model to obtain the similar bound. So you can also get.
So it's like so you have a sum of kernels with the like shadows estimation of the metric, right? So for that one, like if I want to learn the states,
it's
then
very
that means I have to learn the metric, is it?
You just need to learn this part.
This part.
Yeah, you just need to write some actually you can decompose the kernel into two parts. One is the representation of the new input. Another one is the representation of the original training examples. And you can extract this part in the front side, and the rest part is the parameters you need to learn. So you can easily transform this kernel method to a regression model and find the optimal parameters you need to learn. Actually, this model, I mean, this part represents the optimal parameters if you use a regression model. Yeah, we explicitly write down it.
Right, but this one is to learn the properties, right? So if, for example, I want to learn the dense matrix representations and to extrapolate, then that would be very hard, right? Because now the matrix will be exponential in size. Like it's maybe like the sigma. Yeah, this one.
Because this is our best estimator. Maybe for each example, it has some difference or deviations of the target predict result. And this variance depends on the what type of graphical shadow you applied. If you applied Clifford-based shadow, the variance will be very small, and you can say that the reconstructed predict state is almost same with the target predict state, but the price to pay is that memory storage will be very large. A good thing is when you use poly-based classical shadow, although you have maybe a large variance, but it's very efficient. This is a great condition to ensure your computational cost very low or is very efficient.
Right. I see. It's computable. But do you think it's good to convert or like to a learning problem, or do you think this is already the optimal model? Or this one just like show that okay, there exists one set of parameters, for example, that allow you to do efficient learning. But then do you think like adding, like for example, in the slides, you say that okay, it can be converted into a learning problem. Do you think this conversion will help in improving the results, or now it's already kind of optimal?
Based on the first two summaries, we know there do not exist an efficient algorithm that can be used to predict any secrets. So we need to focus on specific class. And in this case, in this problem, I mean the proposed learning model can only apply to the secret satisfy this condition. Maybe sometimes you can devise another model with more mild condition. You do not need to require the gradient norm should be upper bound. Maybe you can find more mild conditions. So this is open question.
Right. I see. Okay, there are some other things that can do.
Yes. I have a question about the truncation of the kernel. You mentioned if I could, you're truncating like high frequency terms.
Yes.
What do you
have high weight as shown here.
High weight terms, okay. Then you are assuming that X follows a uniform distribution, and in that case, you can do the truncation.
Yes.
But how about it's not the case?
Then we cannot apply truncation. This is a big problem. So this is why in the last slide, it's our question, how do we devise a learning model can apply to different distributions of uniform distribution.
Oh, right. But can you just use some randomization or add a random phase to the X and convert your worst case to some random place, and then the target may not coincide with your worst case?
It's an interesting point, but currently don't have any result about this.
Okay. So the worst case problem is the problem of the truncation of the learning part, which is causing the open problem of worst case.
In the worst case, actually you can set up a very difficult circuit and you can use the result of complex theory to prove that if you can efficiently it, then they like equal p belongs to p or maybe some other contradiction of the complex theory. So worst case, in the worst case, I think we do not have an efficient classical learner to predict the results. Otherwise, the advantage may disappear.
Makes sense.
Yeah, actually, I have a like follow-up question on this. Not too sure whether you're referring to the same thing because like now when we speak of like this Fourier series, polynomial expansion, trigonometric monomial basis, there's some way to approximate. One is of course truncation, the other one is through random Fourier series. Random Fourier feature, do you think that could be applied over here as well?
Possibly, but one issue is that I think random Fourier feature has some limitations. So this is why we didn't use the result of random Fourier analysis feature in this work. It's a good direction we can discuss later.
Right, I see. Okay.
Sorry, I also have a question. I do enjoy the theoretical part, but my question is about the numerical things. Because you submit something a large system, 60 qubit G-d state. So and I do wonder that, for example, do you also try for some other heuristic methods to see whether the performance is need to be better, or is it which method is better?
You mean which method?
I mean, for example, compare with the theoretical method.
Theoretical, you mean?
Yeah, I mean, for example, like the kernel-based method, as you consider in the theoretical aspect.
Yeah.
Yes.
This is the values. This one.
Yes, I mean, so I wonder because somehow you have a large data set, right? And that's why I wonder, for example, from the classical machine learning experience, sometimes the multi-risk method can outperforms the theoretical guarantee method. Yeah, so did you also have tried this kind of thing?
We didn't try it because we already know is that if the values is shown here, we can go minimize the prediction error. I know what you mean, but I think
yeah, I mean it's slightly out of the direction, yeah, but just because you really some large quantum state in my mind, so I just had this kind of wonder.
I think what you mean is like some classification task, your optimal result maybe like 80%. And if you use this method, maybe you can get maybe.
Yeah, so for example, as a benchmark, maybe we can consider a gap between the exact value and between the prediction and based on the same training step, something like that.
I see. Good.
This is actually a question for me for this kind of theoretical works, and especially for the learning phase work. So I mean, Robocon has another work which predicts the phase of the Foster Hamiltonians. I do wonder because I mean, for example, as a theoretic, once we show some place that there is a place for efficient learning, and I think there is a place. I mean, there has a larger space, question which you can solve maybe with some first method, and that's what in my mind. Yes.
Yeah, but there is a difference between the classification and the regression. And in this work, we only focus on the regression problem. Maybe for the classification, we may have some new results. Also, for many tasks related to conceptual learning, it can be categorized into the regression problem. It's very difficult to find a classification problem. So this is different from learning the properties of ground states.
Maybe I could ask one last question. You mentioned about the complexity, computational complexity result, right? The heuristic. Polly, could you explain on that a bit more? And yeah, you have a slide on that. I forgot which slides actually.
Yeah.
Yeah, the one with Ricardo's or the Aiden.
I didn't post the whole definition. It's very long. So-
Yeah, I roughly know the definition actually,
Yeah.
but like just wondering, what do you consider in that? Like why do you use that? Actually?
Because occasionally we found that they argue the same thing and we consider. So we just use their results to prove our aim to.
Yeah, this one.
Okay. Because his work question the capability of the classical learner. If very focused on this setting, I mean the robot's results, and all of the related proofs in his work can be easily adapted to our work. So we just leverage their results to show our purpose.
Yeah, so you guys show that it's hard for the classical learner to learn.
Yes.
In the offline setting.
Yes. Yes.
Oh, okay. I see. And because I read their papers and also they go into the proof as well, and I think they're kind of clever in like trying to translate the computational complexity things and then into the learning bound.
Not really just map a problem into a Boolean function and use the hardness of learning this Boolean function to show some computer hardness.
Yeah. So you guys also show it over here basically, but this, like for example, if you let the machine learning algorithm actually, this is what they call quantum learning. It's like in the inference states that allows the kind of the extraction of information, further information, then you can do prediction. So like I think the similar thing could kind of like be given over here, because like if you for example consider the online setting, I'm not too sure whether it's right word, online setting, then you can access quantum computer in the inference space, and then I think the exponential computational time could be lifted. Okay. Then okay, I think it's like we have like many good questions asked. So thanks again, Yuxuan, for the very interesting talk. And if you have any question, feel free to email Yuxuan to ask about it. And thanks everyone. That's